Hello, class. I'm going to walk you through the first lab, Helmholtz Resonator. So I'm going to begin by sharing the screen and bringing up the lab itself. Here it is, Laboratory 1, Helmholtz Resonance. This will be done during the week of January 31st. You're going to do it online Zoom, but during the same time with all of your classmates in your section. So you're going to work in section 1 through 6. You're going to join during that time period. So there's some, I want to go through the experimental procedure and discuss the kind of equipment you're going to have to bring with you to the lab. Okay, so you're going to need an empty bottle, so a empty bottle like, like a plastic drink bottle is fine. I'm going to use a wine bottle, things I have around that's very common. You're going to, and that this empty bottle is going to be your Helmholtz resonator. It's good to have a long, straight neck. So that's why I like this kind of wine bottle. A Bordeaux bottle has a good straight. You need a neck. You need a graduated volumetric. And so a graduated volumetric, I use just a water bottle that has markings on the side to indicate the level. And I give instructions on how you can make your own graduated cylinder if you need to, very simply. You need a ruler, and I use a tape measure that has units of centimeters, on it. And you need a funnel. I'm using this coffee filter, but I show here in the instructions of the lab manual a way to make a funnel with a pair of scissors out of just one of these empty plastic bottles that are pretty ubiquitous. You need to install phyphox on your phone, and I'll show you, we'll walk through that software. And then there's a MATLAB script that will be used to analyze your data. I'll have a separate video on that. Okay, there's two primary objectives to this lab. First, it's going to measure the speed of sound using the Helmholtz resonator. And the second, we're going to compare the measurements of the wavelength of sound that emitted from the resonator as a function of height of the volume of air in the resonator. We're going to compare these measurements with two theories that describe this resonant phenomena. Okay, and then yes, so I'm going to stop the screen share and show you one of the bottles. So here's the bottle that I'm going to use. And so you can see it's filled with water to this high level. If I zoom back a little bit, then you'll see that the bottle is filled with water up to this kind of height where you have the neck and then the top of the bottle. So I'm considering this 100% filled because the meniscus comes up to just to where the cylinder starts getting reduces in diameter to the neck. And so the cavity of the Helmholtz resonator is this part of the bottle that's all filled with water. So the volume of air in this resonator is 0. This amount of air doesn't count as air in the resonator. This is air in the neck. And so the air in the resonator is 0 because it's completely filled with water. Now the question is, what is the volume of air in the resonator when it's emptied of water? That's where the role of this graduated cylinder comes in. So this is a 1 liter water bottle. It has convenient markings on the side, but you could make your own. And so now I'm going to carefully pour all the water out of this resonator. So then it will be filled with air, and I'll know precisely the volume of air that's in this resonator, because it will be the volume of water that's in this graduated cylinder. So let's just do that carefully. We don't want to spill any of the water on the computer. That would ruin everything quickly and be an expensive disaster. And so I pour everything that was in this bottle into my graduated cylinder, and then I can turn it. And that line over here is 900 mils. It's up a bit higher. It's 1 liter. So there's exactly 1 liter of product in here, and you can see that's kind of what it says on the bottle: 1 liter. So it's a 1 liter bottle, and it's filled with 1 liter. And so then the next thing we want to do is create a Helmholtz resonator. So we're going to blow across the top of this like it was a flute to get that very deep sound. If I turn sideways, then you can kind of see the see how you kind of extend your upper lip over the open rim of the bottle. And you blow and you get that sound. And so the next task is that we want to measure that frequency of sound. And so to do that, we're going to use an app on the phone called phyphox, and we get let me see if I can maybe turn down the intensity in my phone so that it doesn't saturate the camera, and that might, I don't know if that will help. So it's a little clearer, I think. So you see this app, phyphox. And we're going to be using these 2 functions down here at the bottom, this one called audio scope, and then the one audio spectrum. Those are the 2 that we'll be using in this lab. And so to demonstrate the functions of this, I'm going, there's I'm going to first do this audio scope. So now I've selected this audio scope function, and then it's recording the amplitude of the pressure of the sound waves versus time. And there's a screen share function called enable remote access. So down here, enable remote access. I'm going to push that, and then that will allow me to use a browser, and then I can type in that URL on a device, and I can display it on that remote device. So let me do that now. I'm going to share the content on a screen that will then I'll share that with you. Here it's coming, and so then I'm sharing the screen. And so if I go to the browser, okay, so then here's the browser being shared on the screen, and you see the, make it a little smaller, so it's phyphox audio scope. This is the amplitude of the pressure waves of my voice hitting the microphone on my iPhone, and so then we see these oscillating waves. And so now if I blow into my, and it's 10 milliseconds duration, I'm going to change this to, what am I doing? It's, I'm clicking on the wrong screen. I'm going to, on my phone, type in 100, whoops, 100 milliseconds. So now you see it says 100 milliseconds. So this whole duration is 100 milliseconds. 1,000 milliseconds is a second, so 1/10 of a second going across here. And then I'm going to blow my note in my Helmholtz resonator. And then I push stop on the app and I stopped it. And so now you see I have how many oscillations, this periodic, because I had a single tone. I mean, it's a very periodic oscillation of the pressure in the sound waves in the air. And so if I have one, and so here's the maximum pressure again, maximum pressure again, maximum pressure again. So the maximum pressure is repetitive, and then this is the minimum pressure, maximum, minimum, maximum. So that's this oscillating frequency between maximum and minimum. The time period, this is time in this axis, amplitude of the air pressure in this axis. The time interval between repetitions is called the period. 1 over the period is the frequency. So how many seconds between here and here? Well, a good way to get accuracy is to count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 peaks going across here. And those 10 peaks take place in, this starts about, I don't know, 2, 3 maybe milliseconds. And this is like another 3 short. So that's 3 plus 3 is 6. So from here to here is 94 milliseconds. And so if I have 10 peaks in 94 milliseconds, then this is 9.4 milliseconds in between each maximum. Okay, so that's nice. I've measured the period. And so if I then go to my lab, I return to the lab. So here's the lab. And in the lab, there's a table of things that we need to occupy ourselves with. And so in this first measurement, where I'm measuring the sound coming out of my Helmholtz resonator, the volume of air, since it's completely empty, the volume of air in the resonator is equal to the volume of water in my graduated cylinder, because I started with a filled, with the resonator had 0 air, 100% water, then I emptied it. And so the volume of this resonator is 1,000 milliliters, so 1 liter. So I put down 1,000 milliliters in that figure, in that. And then my period I just measured was, what did I say, 9.4 milliseconds. And so 1 over 9.4 is about 10.6. So that should be, if I do the math correctly, about 106 hertz. So 1 over the period is the frequency, and that's in 1 over seconds, right? 100 hertz is per second, 106 cycles per second was kind of that sound. And now there's another way of measuring using phyphox, that's called using a spectrum. So let's go to return to phyphox. Here we are again. And now I'm going to pick up my phone, and I'm going to go back to phyphox, to the, I'm back to the menu, and I'm going to choose the one down at the bottom here called audio spectrum. So I'm going to push that one. And then I'm again going to go enable remote access. And then I'm going to play that. And I think I have to update, Okay, there it is. I've updated my window. So now I have a new window. This is now measuring something called Fourier transform. And so this is measuring frequency. So frequency in this axis, and instead of time, it's frequency. And then this is the magnitude on a logarithmic scale. And so if I blow into this now, you see there was a peak. Let me blow and then I'll freeze it. Okay, so I froze it, and you see there's a peak here, but it's not very sharp. And that's because I'm only using very few samples. I'm only measuring at very short intervals. And so if I go up here to settings and I click on that, I click on settings. Maybe I have to go back to audio, make it live again. And if I go to click on settings, so it's not updating on the shared device, but on my phone, I'm clicking on settings, and then I'm going to click on, it comes up when I click on settings, I'm going to click on 32,000, the number there at the bottom, 32,768. I'm going to click on that one. And then you see it updated here, 32,000. So I get much, much finer. And so then I go back to spectrum from settings. I was on settings, I went back to spectrum. And so now I'm displaying the spectrum. And so if I now blow my resonator again, okay, then I've gotten, you see it's a much, much sharper peak, and I'm getting 105.47, 105.5 hertz. And so if we go back to our lab notebook, then it was 105. And that was very close to what we got from the measuring the time response. So, and then the final column over here is height. And so if I unshare screen, let me unshare screen in, I'm going to stop share, okay. And there we have it, we stopped share. And so the last entry was height. So that is going to be the height is going to be the height from the level of the meniscus. In this case, there's no water, so it's going to be the height from the bottom all the way to the very top of the bottle. And so that's the height. It's the height from the level of the water to the top of the cylinder. And if I look at that, it's 31. I measured from the bottom all the way to the top, 31 centimeters. And so if I so I'm off screen, but let me write in 31 centimeters just so I don't forget that. And now I want to take a second measurement. And so I'm going to add some water to the Helmholtz resonator, and that's going to remove some air. So I'm going to reduce the volume of air in the resonator. And so I take my funnel, and I'm going to pour in, I don't know, like 200 mils. So I'm going to pour it till it goes down to like, well, I poured in a little more than I wanted to. It's around 780. So let's take a look there. we go. So you see I've poured now some water into the, so I raised the meniscus, I displaced air out of the resonator. The amount of air, the volume of air in the resonator is kind of the volume from the meniscus to this level here to where the bottle reduces in height. So that's the new volume. That new volume is the volume of water that remains in the cylinder because I removed a certain amount that displaced the air. And so this volume is, you can see the meniscus here. It's a little bit, it's a little bit above, it's like 780, let's say, 780 mils. And so then, and then it makes a certain tone. So now let's go back to the shared screen with the share content screen and start broadcast. 3, 2, 1. Now, okay, I'm broadcasting. And so here's our lab notebook. So I had entered 31, and now the new volume was something like 780 mils. So I entered that, and now let's see what the phyphox says. I'm just going to use the audio spectrum, and I'm going to go to the remote. Let me go to the remote here. And it's phyphox such as changed. You want to reload this window? Okay. So now here's the reloaded window. And so then I'm going to blow on the bottle and see what the frequency is now. I didn't stop it. There, I captured it. And you see this very sharp peak. Now, these are logarithmic scales. So every time there's a band like this, the amplitude of that frequency is increased by a factor of 10. So from this level to here, that's a factor of 100. Okay, so this is a logarithmic scale. So you have, and this is also logarithmic in frequency. So the frequency changes just a little bit, and the amplitude changes by 100. So on this logarithmic scale, it's saying that the sound is a very pure, a pure resonance, a single frequency, and it's 115.72. Let's call that 116 hertz. 116 hertz. So that's over here in the spectrum, 116. And then you can repeat the measurement with the audio scope to get the period and things. And now what is the height? So now the height is measured from here, the level of the meniscus, to the top of the bottle. So if I tilt and move out, it's, I know the screen is very small because I'm sharing screens, but I measure from the height of the meniscus, which is there, to the top of the bottle, and I'm getting 26. So 26 centimeters. And so I write that down over here. And so now I've measured the height, I measured the volume, and measured the frequency. So this is what you want to do for about 10 different values. And then that's the basic data collection. So now I'm going to stop sharing screen from my iPad, and I'm going to share screen from my computer. And I want to, and then so you go through and you do these measurements, the height of the air in the resonator is measured from the level of the meniscus to the top of the bottle, and the volume of air in the resonator, which we consider as only the main part, not from the neck up. This part here is given by filling the bottle with the water up to where the neck begins, and then pouring it into the graduated cylinder. And so that volume of water in the graduated cylinder is the volume of air in the resonator. And as you pour water back out of the bottle, so then reduces the volume of water in the graduated cylinder reduces the volume of air in the Helmholtz resonator equally reduces. And so you can just read the level of the water in the graduated cylinder. It gives you the volume of air in the Helmholtz resonator. And then in the write-up, after you've taken your data, you're going to do various plots. The frequency versus 1 over the square root of volume, frequency versus the height. And then, so then there's some MATLAB scripts that will help you with that analysis. Those are online, and Helmholtz resonator. And then you're going to enter the data, the volumes that you measured, those frequencies that you measured, the heights that you measured. You enter that data up here. This was data from experiment I did with my wine bottle. You'll have your own bottles, so you'll edit that. And then there's various kinds of analyses. I'm going to have a separate video walking you through these analyses. But at the end, you come to this point where you have your measured data of wavelength versus the height of the air in the resonator. And depending on whether or not it's a standing wave phenomena like an organ pipe, that would be this theory, or the Helmholtz resonator would be this one. Depending on the size of your bottle, you'll be closer to one or the other. And so here's a picture of Helmholtz, 1862. This picture was taken holding one of his resonators. And so do a good job on the lab and make Helmholtz proud. So thank you. I hope you'll enjoy this lab as much as I did. I had a lot of fun developing it. It's challenging doing labs remotely, but this phyphox app is just great, and really takes your iPhone and makes it into a super sophisticated quantitative physical instrument. And there's so much you can do with it. It's a lot of fun. All right. Good luck with lab. Bye.